or maybe we should say, let's finish this. So the semester is finally almost over. This is the last lecture. So this announcement. First, I don't have the projects graded yet, so I've graded maybe a third to a half of them. I'm hopeful I'll have them by Wednesday, and if that's the case, I'll have the TAs. We'll have them and can hand them out to people individually during the poster session. If not, I'll figure out some way to kind of get the grades and feedback back to you. So just let me write a reminder note. The poster session. Over there. Okay, so it's going to be this Wednesday, April 23rd. It's going to be in this room. Okay, and we've got the room officially from 5 to 7 p.m. Okay, so I made sure we have it a little bit longer. So if you can only make it from 5:15 to 6:35, that'll be okay. But there are 33 posters, I think, and so see that leaves me about a little under 4 minutes per poster if it's 2 hours. So I have to get to all these. So just if you can try and plan to be here this whole time, that'd be great. So as far as the posters go, I think 25 or 26 of you have had them printed. I talked to Chris Coleman this afternoon, who's printing them. He said that everyone who sent them to him by, at least by over the weekend, the posters have already been printed, so that's good. So even if you're a little late, you still got it printed. Someone sent it to him Monday afternoon. That one may or may not be printed yet, but it'll probably be printed. The posters will be delivered here in this room. We'll try and get them here by 5. There will also be some easels and some poster boards to put up, as well as some magnets, so some people can put them up here on the whiteboard as well. And then, I don't know, maybe there might be some tacks you can use on the soundproofing stuff there as well. But just don't do anything that looks like it would permanently damage the room, or I might get in trouble. But feel free to use anyone in the room. If you spread out, I think there should be enough space. But it's when people sit in the room, it feels more spacious than if everyone's standing. So it'll be kind of packed. But it should be good. If you're had it printed by the department, all this stuff will be here. Even if you print it yourself or have another way of doing it, we'll hopefully still have enough easels and poster boards so you can clip stuff up on there. So again, Wednesday from 5 to 7 p.m. And when you get in, the TAs will, you'll need to pick up a little sheet of paper with your name on it, which will have, actually I'll probably just have one piece of paper that has everyone's name on it, and they'll have 2 posters that everyone is assigned to that you'll need to go and look at those and write up like a short summary of what was in the poster. And so before you leave, you need to turn those into the TAs. Okay, so there'll probably be a pile of them, and you can turn them into a pile. So that, and then the last thing is you will get to vote on other people's posters. This is worth either 10 or the first place poster will get 10 bonus points, and towards the poster part of the grade, and the second place one will get 5 bonus points. I encourage you to kind of have a very cool presentation for your poster to encourage other people to vote for it. It does not need to be one of the 2 that you've been assigned. It can be anyone. So, if I'm not near your poster, go and look at other people's poster. And then finally, I'll be going around to all of the posters, and I'll have, like I said, roughly 3 to 4 minutes per poster. So prepare like a 2-minute overview for me, where you give me a 2-minute spiel of what's on your poster, explain it, and then if, you know, some of you will probably go over that, and please try not to, but then I will probably ask you a few questions about the poster as well. You will do better if you don't go over the 2-minute time. And if you want to have one person in your group do most of the presentation, that's fine, but I may ask questions that of someone else in your group. All right, so any questions on the posters? Okay, so it should be a lot of fun. There's lots of interesting stuff. Different groups have worked on kind of different attacks on similar problems, so you'll kind of get to see a very broad spectrum of techniques. I think just about everything we discussed in the class was worked on by some projects, so you kind of get to see a lot of the stuff in action, so it should be pretty cool. So cool. So this is the last lecture. So I just want to kind of remind you that you should fill out the instructor on the instructor evaluation forms, and you know you should tell the university that I did a very good job, hopefully, or if you don't think so, feel free not to fill out the form. If you don't want to, if you want to fill out the form, that's fine, but I would appreciate it if you gave me a good score. So the last lecture will be on graph sparsification. But before we get into this, I just want to quickly kind of, because we don't have a final exam, and the poster session will kind of overview everything, but I kind of want to give just a quick summary of everything that we talked about in the class, and maybe point out some things that you hopefully learned, even though you may not have realized you were you actually learned in the class. So when you're doing data mining, remember, often, and as hopefully you found out with your projects, is you start off with some messy data, and it's been collected in some way, and you don't, it's in some format which is not necessarily the format that you want to work with, and you may not know initially what to do with it, and so the first thing that we talked about, and we talked about various things, is converting into some abstract data format. And so this included points in RD. This included sets. These were like when we were talking about converting these documents into these sets with the k-grams. There was these matrix representations and then the graphs. And so once we were in one of these abstract types, then each of these had some very specific, some algorithms. And there were different sorts of things we could run on, but they were meant for one of these abstract types. So your data did not come necessarily in one of these formats, and we needed to move it here. And so this included a lot of modeling. So there were choices you made here, and this adds some form of noise into the data, and some of that's your choosing. You say what part of the data you want to look at, which part do you think is not important for you. And you have to make choices here. So anything that you end up doing with your data afterwards, you've made some choice of how you model this data. And you need to think about this and how do you affect this. And then we talked about a variety of these algorithmic techniques. Certain of them, as you found in your, as I told you in class, you did the homeworks, or in your projects, you found some worked really efficiently on large data sets, some not as much. And they gave you different trade-offs between what scale, the scaling versus the modeling. So you can do much better modeling on clustering with, say, the hierarchical clustering, but often this didn't scale nearly as well as some of the variants of stuff like k-means, right? So you end up trading these off, and depending on which format you came in here, you had different amounts of modeling and allowed you to scale to different levels. So these were choices that you had to make along the way. Okay, and so some of the things that I think people had some trouble with in class, I I presented some algorithms in some kind of these more abstract settings, in like some pseudocode. And sometimes I didn't present every last detail of how to do this. Well, and hopefully I will, through feedback and questions, you're able to figure this out. If you're going out into the world and you want to be a data analyst, a data scientist, you're going to be getting data here. You're going to be making these modeling choices to get to some abstract format, and then you're going to have to choose which algorithm to apply. Now you can go back and look at the notes from my class, I'll leave those online, or your personal notes or whatever, or you may end up saying, what is the state-of-the-art way to do this? You're going to have to find a paper, and it's going to describe it in some abstract format. And so these are the sort of skills you'll need to have in order to actually go from the messy data that you start with in order to actually kind of perform some sort of analysis on it. So hopefully you've gotten a taste of this whole pipeline, and so I'm kind of, hoping that you take that away from the class, that this is kind of this steps of how to do this, and hopefully you've gotten a taste of lots of different areas. We kind of went over a lot of the basics and these different techniques, from clustering and regression to similarity search, and also some more things on the state of the art, kind of cutting on the last few years that have been coming out. So, we can't cover everything, but hopefully you got an interest and taste of the sort of things that are out there. All right, so, okay, so that was the class in a nutshell. Then the final lecture, again, say, is on graph Sparsification. Okay, so again, we can think of often we write a graph as a set of vertices and a set of these edges. And you'll say that often the number of vertices, so the equals n equals the number of vertices, and the number of edges is m. And so what we're talking about in some examples we looked at is that if you look at the web graph, or if the number of pages, web pages in the web graph may have been maybe up to something like 1 billion. And the number of users on Facebook is now over 1 billion. They may not all be active users, but they have 1 billion users on Facebook. So we have this huge number of users, and we've kind of said that, I give you this number, that the average number of links in a web page was maybe 20. Right? So then that means that the number of edges may be roughly 20 billion. And so maybe we could think that this was actually some constant times the number of vertices. Okay, so as the graphs grew, that the number of edges would kind of grow linearly with the size of the graph. Right? So, if we got up to 10 billion web pages or 10 billion Facebook users, maybe the world population is 10 billion in so many years, and everyone is on Facebook. Right? So let's say this came up to 10 billion somehow. Maybe some people have 2 accounts. Right? So we're up to 10 billion pages. Hopefully, we've only got up to 200 billion edges. Maybe that's reasonable. And so the computing equipment will scale and so forth, and maybe we can still handle this all in the same way. Well, it turns out that this kind of assumption, and this has been kind of assumed, that there's about some constant number of edges for every node in the graph as these graphs grow, that's turned out not to quite be true. So it turns out that a better model of looking at this has been actually that the number of edges is going to be roughly the number of vertices for 1 plus, to the power of 1 plus gamma for some constant gamma. Okay, and gamma is in the range of 0.1 to 0. Say, yeah, I've seen as high as 0.5. Right, so there's been some various studies. They have looked at some graphs as they've grown and tried to figure out, you know, what, on various graphs, if we were to fit a model, that this is kind of a model, and depending on the graph, it's somewhere in this range. Okay, so if this is 0.5, that means that for every vertex, there's going to be a square root of 1 billion edges. What's the square root of 1 billion? That's like a few...
34,000.
Oh, like 24,000?
34.
Yeah, so, no, this would be like, so if you think of this to 1/2, or let's say 1 billion, this would equal about 24,000. So that would mean think of this, over the lifetime of your Facebook account, maybe you would interact with, message with, or visit in some way 24,000 different other users. As these networks grow, people they move from community to community, they grow, they interact with more people. You know, maybe this is not the ratio of Facebook, but it's definitely the place in other social networks. So you think on Twitter, so you probably don't follow, you know, maybe you don't follow too many people yourself, but there are some people who follow a ton of users and use this as kind of as an aggregator. At the same point, there are certain users who have a ton of followers, like the CNN account has just a really large number of followers. So, you know, how is this, you know, is this the feasible way of scaling? So if you're trying to model one of these graphs, and this is growing super linearly, are the same sort of techniques going to work? Are we going to be able to kind of work with this graph in the same way we have before? Okay, so the problem of graph sparsification is to take a graph and assume that it's following some pattern here, where the edges are growing super linearly with the number of vertices. And the goal, okay, so the goal here is to get the number of edges in some prime graph. So we have H is going to be another graph, it's going to have the same vertex set, but the edge set is going to be prime. And will probably be a subset, but we may kind of change the weights or do some other stuff, so we'll just call it edge prime. And I want this to be roughly some constant times the number of vertices times the log of the number of vertices. Okay, so I'm not going to quite get down to kind of linear here, but this is going to be a log term instead. So hopefully this is going to be more reasonable. So I mean, it'd be nice if we can get down to just some constant times number of vertices, but kind of the theory of the approaches we're going to talk about are going to get us down to some constant, which will depend on some approximations we're giving up times the log of the number of vertices. Okay, and so when we do this, it's not the original graph, but we want some of the original properties. So we want the properties of graph G approximately. Okay, and so we've talked about various properties of the graph. So we're mainly going to be talking about properties having to do with graph cuts and then generalizations of this, right? So we're thinking of, if you're trying to divide the graph into two parts, say you're finding some communities or clusters in the graph, how well do I preserve the number of edges that I'm crossing? And then we'll talk about some generalizations of the notion of cuts as well. So this corresponds kind of with, so you know, if we're doing clustering on the graph, we're finding these communities, we'll see how it kind of relates to if we're doing some random walks on the graph, it'll be kind of related to that. But it'll be specifically tailored to the cut property. There may be other things you can do to, say, try and preserve like the betweenness, the approximate betweenness in certain ways, or specifically the PageRank vector. So they're actually fairly different techniques for the PageRank vector, but I'll mention some of these approaches. So any kind of questions on the rough problem we're talking about? Okay. So, so before I get started, kind of one common idea in sparsifying a graph is this, and now, you know, it's going to be hard to draw pictures which really illustrate this. This really only makes sense on a really large scale. So, you know, I wanted to get to something like this constant is 20. I'm probably going to get to something like this constant is maybe like maybe 100, and you're going to also have this log term here. Okay, so I'm not going to do quite as good, but I want to get below something that looks like this 24,000. And so this is, so, you know, so there's kind of some neat connections to other stuff we've done here. And I think these algorithms work a little bit better in practice than the kind of the worst case guarantees I'll tell you about, and I'll kind of explain those. But the guarantees are not going to look as kind of exciting as you might like. And I'll tell you some other techniques which kind of heuristically might work a little bit better in different scenarios. In addition to these techniques, which I think will work a little bit better than the theory will tell you that. Okay. So the basic idea is, so the first cut of this is if you think you have a graph and your goal is to preserve the communities in this graph, then the communities should have a lot of edges between them. And then there should not be too many edges in between these communities. Right? So you may want to say, well, if I really have a lot here, I can find these communities, okay? And then I can say, well, I'm going to keep these edges here. And then inside the communities, maybe I don't need all of these edges. I just need to say that this is connected. So, you know, think of this, I've drawn it at a much smaller scale, but if there's a really strong connections here, I probably don't need all the edges. I can kind of upweight them and kind of know that there's strong connections inside these groups. So this is kind of how some heuristic techniques work, and this works fairly well in an abstract sense. But the problem is, it's kind of a chicken and egg problem. In order to find these communities, you've already kind of you've already solved some of the problem that you were hoping to avoid having to solve on the full graph. So if you can already find these communities, then maybe you don't even need to sparsify in the first place. So there's kind of some rough approaches that work this way, but this is kind of, the problem is you first need to find the communities in order to do this. This is kind of limited in really helping you do scalability, but this kind of tells you about the sort of structure that we'll want to do. We'll want to keep these important edges that are going across and are capturing the kind of inter-community relations, and we can kind of approximate this denser region where there's lots of edges. We don't need to keep track of all of them. Okay, so this is kind of one main idea. I'll mention there's another area called graph compression. And I kind of mentioned this when we were talking about doing PageRank on top of MapReduce. And that was the idea that, well, these number of links are growing to some extent per web page. I mean, if you think about why this is, it used to be that each web page had to be fairly simple because if you had a really complicated thing, it would take a long time to load. And so people were keeping them simpler, and now you'll see a web page, and it'll have a bunch of stuff on the header, and there'll be a bunch of links here. You'll have a sidebar with a bunch of these links. So you now have a bunch of links up here, and a bunch of links here on the sidebar, and then you may have some links scattered in kind of the main content. And so, you know, it was less common to have such a big header and sidebar because people's screens weren't as big, it took longer to load. So this is kind of a newer approach, and this is why the number of links per web page has been actually growing over time with respect to the number of links per web page. Yeah. But there's another phenomenon, is that you'll get a lot of web pages that look exactly like this with the same form and the same links here and the same links on the top. Okay, so what that means is that you can compress this. All the web pages from a certain form, you don't really need to store them independently. So you can kind of compress the format of all these links here. So you can compress this form, and then if you discover this form, a lot of these may link out to the same other sites, right? So if you're looking on someone's blog and they have a separate HTML thing for every post, and they have a sidebar with links to their favorite other blogs, something like that, well, they're all going to point out to the same thing. I just kind of need one representative from this whole set of web pages here. So I can get this, I can replace this with one supernode. So instead of having, in this case here, kind of like what I've done in this picture, I can kind of have some representation inside, which I can probably compress, but I need to keep these links going outside. There are certain important links that I don't want to get rid of. So I want to identify these supernodes that I can compress something inside of here. And this is still keeping, this can be a lossless compression even. I don't need to store as much information. I can say it's part of this form and store all the links generically. But what I'll be talking about is a lossy compression, or where instead I'm going to actually throw away some links. I'm going to get an approximate property instead of the exact property. So the exact property that I want is that I'm going to think of every edge, and we'll call this, let's call this edge in the edge set, and the edge will be equal to ij. So it's a link between nodes I and node j. And so I want to look at some cut, which is equal to st, where s, so this is a cut, where s is a subset of v, and then t is equal to v minus s, right? So I've partitioned the nodes into these two parts, so this is a cut. And so then I say that the edges in the cut, so an edge is in cut st if I, so say edge ij, if I is in s and j is in t, or if j is in s and I is in t. Right? So that would do where I have this graph here in this picture. If I did a cut like this, so then you just label this as s, and everything else over here is going to be t. And then the edges in the cut are just going to be these three edges, are going to be, these three are in cut of st. Okay? And so now, I'm going to initially start with every edge having a weight of 1. So So for the edge set, I'm going to have, so for every edge in here, I'm going to have a weight of this edge equal to 1. And so then in my new edge set, I'm going to have a weight, so I'm going to create a graph H, same vertices with different edge primes, and each E prime in E is going to have a weight. And so this weight is, is not restriction. It could be greater than 1, it could be 0 if the edge does not exist. Okay, so this is going to be a weight. And so I'm probably going to have that, and so actually, we'll actually normalize this way here. It'll be simpler to write if this is 1 over the number of edges. Okay, and so we're going to have that the sum over edges in E of weight edge is equal to 1, and also the sum over edge prime in E prime, this is also going to be equal to 1. So we've normalized the weights. It's easier to write what the goal is. And then what we want is that for any cut, we're going to have that the sum of edges in cut ST minus the sum of edges prime in cut ST. So these are the edges in E prime. I want this to be less than some parameter epsilon, and this is some parameter less than. Okay, so I'm going to set some error parameter. So this is my error tolerance. Okay. So now if I set, okay, so let's look at this. So if I set this error to be, so this is 10%. So this error is 1 over 10. Then I say that if any cut goes across, I'm going to be off by most 10% of the edges if it goes across. So this bound is not really that strong for most epsilon. It's saying I have to have, if I was off by most 10% of the edges in just this cut, then I'd be violating this property. But what's cool about this is it holds for any possible cut. So it means I cannot find a way of subdividing the graph where I have more than 10% error. But it's really only talking about these really large cuts where this is really, really important, where I have a lot of weight going across. Okay, so we'll see why this will kind of work better in practice than what this is saying. So the cool property is it works for any cut, but the bad thing is it's really only 10% of the total number of edges is how many you're off by. This epsilon is 1/10. And we'll see that this constant of the size we're going to need here is going to depend on epsilon, on 1 over epsilon. So we don't, if we make this too small, then the size of the number of edges we're going to have is going to be too big. So that's not going to be useful to do in the first place. And what we're going to do is we're going to use a random sampling approach of how to do this, but it's not going to be, we're going to kind of make sure that we definitely don't miss out on certain things that are really important. We don't want to miss on the connectivity of certain nodes. So basically, the algorithm is going to be very simple now that we have this definition. So we're going to sample each edge Dij and put in E prime with probability, we'll call it Pij, and I'll define what this Pij means in a second, and we'll have weight prime equals to 1 over P ij. Okay, so if I do this, it means that because I sample each edge with this probability independently, and then the expected weight is going to be the sum of all these, which is 1 over this, so that the expected total weight should still be 1 if I did this. So well, okay, no, its weight's going to be, sorry, is going to be proportional to this. How's this? Let me check my notes. Yeah, okay, so this I've kind of confused stuff a little bit here. This definition was where the weights are 1 over epsilon, so that this error was always less than 1. But really, this definition works when the weights have, the original weights by default have a weight of 1. So let me figure out how to fix this. So this simplest way of how to fix this is actually to say that this holds with probably here, and we just say that the total weight here is equal to, okay. So I changed this error bound a little bit by multiplying all the weights through by. So basically, in the original data set, you usually assume the weights are 1, but if they have a different weight in the original thing, we can still use this by just summing this up to whatever the sum of the original weights is. So if you have kind of 2 instances of the same edge, you give it a weight 2, and then that's the number of edges. So or just assume originally all the edges have a weight of 1, and this one. Okay, and then if we sample them, then the expected value of any of these edges of being sampled is going to be exactly the original weight of the edge, which is going to be 1. So we sample with probability this, and we give it a weight of this, and so the expected weight of